Hi, welcome back. This time we're going to talk about another way to understand functions of multiple variables, and that has to do with level curves. So our goal here is going to be able to give us another way to piece together the shape of the curve of a function or of an implicitly defined function. So when we talk about level curves, what we're looking for is the set of curves of the equations f of xy is equal to k for different values of k. What you should think of here is you should think of slicing the graph of a function by different heights. Okay, so let's look at some examples of different types of level curves that you probably have seen already. So, first one, isothermals. There's my thing here. So if you look at a temperature map, so here's something that you may be familiar with. Here's a temperature map. Uh, there's often these different colors to represent different temperatures, but then there's often these lines along the way that divide the regions that have the same temperatures uh, between each other. So this line here that represents 80 degrees Fahrenheit is the dividing line between being more than 80 and less than 80. And so this line here, this curve, is called an isothermal, but what it is it's a level curve of the temperature function. Every place in the United States or on the world has a temperature, and what you'd like to do is you'd like to say, well, there's a function that takes your current position, latitude, longitude if you want to, and says what's the temperature at that location. And that's a nice function. It takes in two variables, your latitude and your longitude, and it gives out what is your temperature there. And so that's an example. And so drawing these isothermals is telling you where is it where this function is constant. If you're standing in a certain place, and there's warmer places in one direction and colder places in another, there's a direction in which you can walk that keeps the same temperature. All right, so that's one example. All right, another example is the idea of a mountain range map. So if you ever go hiking, then you'll often see these elevation maps. Oops, that's the wrong button. You'll often see these elevation maps where you've got a picture, and if you're trying to understand what it's going to be like on your hike, then you look at these lines, you say, well, what's the height? What's the elevation of the along this path? And you can see these numbers here, this number 1320, I think it's in feet, this number 1590 up here. And what that's saying is as you walk along this path, your height here is 1320, and if you keep going, you'll get up to 1590 up here. And so what this is doing is it's giving you a way to see if you walk along these lines, you're going to stay at the same elevation. You're not going up, you're not going down. So these curves are very helpful in understanding how the terrain is, but it's also really helpful in terms of trying to piece together what the graph of the elevation looks like, right? So if you're trying to graph this function, if you're trying to see what what these curves are doing, if you're trying to understand how the function looks in 3 dimensions, if you have these slices of the same elevation or the same temperature, that's going to give you a good feel for how to piece together uh, the, the surface that represents the function over the domain. An important thing to recognize is that when these lines are close together, the surface is steeper. So in this place, these lines are really close together. That means that as you walk along this path, your elevation is increasing faster and faster and faster. Or in this area, if you were to drive from this part of Arizona to this part of Arizona, your temperature would increase really, really, really fast. But over here, if you start driving, the temperature is really not changing so fast because you can drive all the way from Illinois down to almost to Louisiana, and your temperature will not have changed by more than 5 degrees. So that's pretty. So that's what these when lines are. That's how you can read this map of level curves and interpret in terms of how fast the function is changing. So let's do a thought exercise. Let's zoom in here, and we want to ask, here's a map. I'll get out of the way. Here's a map. What does the graph look like? So what we're doing here is, so this is our domain. The domain is this oval shape, and we'd like to construct what the graph looks like above it. So this is at height 1. This outer part is at height 1. So this is height 1. All right, what about height 2, height 3, height 4, height 5? You should maybe try this yourself. Pause and come back. And so now at height 2, we have a circle that's a little bit higher. Not a circle, an oval. Height 3, I mean, we should also keep in mind this is at height 1 and this is at height 2. All right, maybe use a different color here. For height 3, we've got this bump here, this bump here. So those are going to translate to, at height 3, we've got a bump there, we've got a bump here. And at height 4, you've got this bump here and this bump here. So if we're going to connect these all together, what we see basically is we've got like a double mountain range. We got to go up and down into the valley there and around, and we have this three-dimensional shape. The graph of this curve is made by combining these levels level by level. All right, so at the same time, we can ask, well, if we have an equation, can we sketch the level curves? And if we can sketch the level curves, then maybe we can reconstitute what the function, the graph of the function looks like. So here's this function before that we had a hard time trying to understand what the graph of it would look like until we did a little bit more thinking. So here what we'd like to do is draw the level curves for different values of k. So for different values of k, so if k is equal to 0, 0 equals square root of 9 minus x squared minus y squared, we have to now solve this. What do we get? We get x squared plus y squared is equal to 9. So this is a circle of radius 3. When k is equal to 1, we set h equal to 1. 1 is equal to the square root of 9 minus x squared minus y squared. we get x squared plus y squared is equal to 8. And this is a circle of radius square root of 8. All right, I think I can't go down any further. So here, if I do 2 is equal to square root of 9 minus x squared minus y squared, then this is a circle of radius 9 minus 4, so square root of 5, about 2.2-ish, and this is about 2.7-ish. Not 100% sure about that, but it's good enough for what we have to do. And what about the level curve when we have 3 is equal to square root of 9 minus y? 3 is equal to the square root of 9 minus x squared minus y squared. This is a circle of radius 0. So if we're drawing these level curves, what we would have is we would have height 0 at radius 3. Maybe I'll use a different color here. Height 1 at radius 2.7. Then we have height 2 at radius 2.2. And then at radius, the height 3 would be at 3. And so if we were working to reconstruct this, we would say, oh, so we have a circle here. We have a circle that's a little bit smaller. Let me use the same color scheme as I had over there. So we have a circle of radius 3, a circle of radius 2.8, 2.7, a circle of radius 2.2, and then just a point at height 3. And that's going to give us our shape that is that's a sphere. So let's go over and use Mathematica to draw these levels, these level curves, contour lines. So back over here. So if we want to visualize the level curves, the contours of a function, then what we're looking for is, so Mathematica has this command called contour plot. So if we plug in our function, this is that same function that we had earlier. And what we're looking for is what happens if we slice this function at height 0, at height 1, at height 2, at height 3, at height 4. What are the shapes of those curves going to be? So Mathematica is going in and doing it all by itself. So it's saying, okay, so at height 0, right, this is the domain. The domain is everything that's inside these regions. But when is this function equal to 1? It's equal to 1 along this curve between the dark blue and the lighter blue. And then the function is equal to 2 along this curve between this lighter blue and this gray. And then it's 3 on this curve that goes between the gray and the orange. And so you're reading off the contours from this picture. If you want to specify one particular contour, you can use contour plot, where you just say, I want this square root to be equal to 3. So then this gives exactly that curve where it's equal to 3. And if you have a set of contours that you want specifically, so for example, if I wanted the contour at 1.5, 3, 4.5, and 6, you can also specify those for Mathematica, and it will give you exactly those things. All right, so that's enough for here. Next time we're going to talk about functions of 3 variables and more. All right, see you soon.